Alright, I'm Catherine. I worked with Sareem, Tala, and Thomas on axiomatic design of sheet metal forming, specifically trying to reduce the defects that you encounter in the process. Our proposal is to utilize axiomatic design principles to design a sheet metal forming process that would ideally produce defect-free parts. And the reason we're doing this is because over half of all metal production is done on sheet metal in a forming type process. You can see a few of these examples at the bottom of the page. Car parts, a sink from a very interesting angle, and this one here is for an air conditioner compressor. And usually the process is guided largely by finite element analysis.
So I'll get into the decomposition. FR0, we want to create a process that would form sheet metal with no defects. The design parameter for that would be a cold working system to form sheet metal with no defects. And the reason we chose a cold working system as opposed to a warm working system or hot working system is to avoid thermomechanic elements, heat transfer elements, and things like that. So we labeled that as a constraint. So our first functional requirement is to control the alignment of the blank. The parameter for that is locating pins to align the material. Our second functional requirement is to control surface finish. The parameter for that is a friction-based system to control the surface finish. And our third functional requirement is to control the part shape. And this functional requirement we get into a bit further down in the decomposition. The parameter for that is a stamping process to control the part shape. And also another constraint is the part thickness, which is greater than 85% of the sheet thickness. And the reason we label this a constraint is to get rid of a functional requirement which would have been controlling the strength. So we tackled that via constraint. And if you look at the bottom, you can see the matrix, and it's uncoupled. The second level, we're breaking apart the FR3, which is a control part shape. So 3.1 is to control bending. The design parameter for that is a punch system to control bending. 3.2 is to control the flat surfaces. And the parameter for that is a material flow control system to control the flat surfaces. Just a side note, features such as holes and things like that weren't considered part of the forming. And if you look at the matrix at the bottom, it's not completely, there's coupling at the bottom, and that's due to the punch force, which affects both the bending and the flat surface functional requirements. So.
All right, I'll talk a little more about what we did for control bends. As you can see, for any bend, there are two important parameters which play a role. One of them is the angle of the bend, and the second one is the radius of the bend. So we basically focused more on the on controlling the angle of bend, which can also be labeled as controlling spring back. And going a little more into detail on that. This is all the decompositions we came up with. An important thing is to calculate the process parameters, which are the bending moment and the loaded bending angle. And we use the, here's a visual presentation of that. Controlling the bending, generally what comes in is a punch, there is a punch angle on the, which provides a loaded angle here. Like for example, when the punch goes back, there is a spring back, and the part angle is different from the punch angle. Now, this was mentioned in Namsu's book, The Design of Principles, that the difference in this angle can be calculated keeping in view the Young's modulus and the moment of inertia of the part. And now using these two, using this graph, we can calculate the tool angle that has to be done so that the final angle would be as per the requirement of the problem. Controlling the flat surfaces, there are two major defects that can be characterized with flat surfaces. One of them is thinning. We've already covered that as constraint, that we do not want the path thickness to go beyond 85%. The other one is wrinkling. Now, going into the details of wrinkling, wrinkling comes in due to compressive stresses during the forming process. One of the ways to control the compressive stresses is to restrict the flow of materials, and for that a patent has been used that drying beads are used in the blank holder. Second, an innovative idea that has been used in in these days is to have variable blank holding force, which can be provided through use of a rubber tab material, for example urethane, between two pots of punch. How this works is once the punch is being forced down by the stamping machine, this rubber material compresses and expands outwards. And once it expands outwards, due to friction between the rubber and the blank holder, it increases the force that the blank holder is clamping the part here with. And therefore it provides a variable blank force. Thus, as the punch force increases, so does the blanking force, and that helps in lowering the wrinkling. So,
just quickly going over the entire model. So for the forming process, we have the die punch set and the stamping machine, and that includes the blank holder. So with these 4 parameters, we can pretty much control all the other parameters that's the punch radius, urethane pads, punch angles, speed, punch force, the angles, and the radius. The advantage of this whole system is that so currently, to make a die punch set, they have to iterate and keep on iterating and then perform FEM analysis on that to get a final die punch set. But with again axiomatic design, if you get all these parameters, you can pretty much get a perfect part. So yeah, that's the physical model for that. And these are our references. That's pretty much it. So thank you for your attention.
Questions? A couple of general comments, if I might, while you're thinking. I would like to see some detail on the relationship between the FR and the DP. An equation, a graph, and some citation from literature. Now, you need not do that everywhere. Some of you have got very extensive decompositions, and it would be overly burdensome to expect you to do that on each pair. So focus on something that you can find the relationship for in the literature, and just give an example of how you would do that. If you get hung up on some of this stuff, one of the things to consider is, how would I measure that FR? How would I tell if I had accomplished the FR thing? Because your FRs gauge success in the design. They accomplish so what do I do to measure to see if I'm successful in achieving that FR? All right, why don't we get the next group up here? Thank you very much. Good job.